So, in the previous lecture, we considered adding impurities to our semiconducting system, and we ended up with the following picture. We have a conduction band. We have a valence band. We can have acceptors and donors. So donors are somewhat lower in energy than the conduction band. Why? Because they have an extra electron, but it's bound to them, so it reduces its energy by a factor 100 to the hydrogen atom ionization energy. And we have acceptors, which is a mirror picture. What are we going to do in this and the next lecture? Two things. First, we'll do statistical mechanics of this structure. Meaning we'll try to figure out what is the population in the conductance band, the impurities, anywhere else, just by standard statistical mechanics. And that's something that actually could have been studied in statistical mechanics. We don't have any more ingredients than putting density of states, number of impurities, whether acceptors and donors, and just calculating the probability of populating a state. So that's counting. Then we'll go and do something more elaborate, and this is a case where we don't dope homogeneously all over the system. We'll dope in some regions with acceptors and in some region with donors. And try to figure out what is the physics of this behavior. There we'll see we have additional considerations. And that would be actually the gateway to an interesting electronic device, the diode, which is exactly this situation. And truth be told, also a transistor, different profile of doping. Okay, so until we're down to 4. Okay, so actually we have seen how to treat the conductance and valence band. All we need for it is the density of states in the valence, the density of states in the conduction band, which are not necessarily equal. For example, the shape of the band or the effective mass could be different between those two bands. So GV is not necessarily equal to GC. And then we have these impurities. Now, basically, and for simplicity, we will consider as if we have a certain number of donors and a certain number of acceptors in the system. The number is much lower than the number of the atoms building up this lattice. Okay, we assume that neighboring impurities have no influence on one another. Basically, their density is very low, we can ignore it. So we assume that we have just Nd and Na impurities in our system. Okay, what is the statistical mechanics of these impurities and acceptors? Well, as it should have been hammered into you during statistical mechanics, first, count the states. Second, write down the Boltzmann weight. That's all you have in this game. Okay, what are the possible states in this game? For the donors, I have an additional orbit that is populated by one electron. That's what a donor is. Now, if I'm looking on this impurity, I have actually 4 states that this impurity can be in. So I'm considering it as one state. And this state can be actually unpopulated. Populated by one electron. We spin up. Populated by one electron. We spin down. And populated by 2 electrons, spin up and spin down. So I have 4 states, actually the same picture exactly for the acceptors. Okay, I want to simplify a bit what's happening here. What is the most probable behavior for the donor? We are considering finite temperature. It's either the electron remains here or the electron moves up. You could argue that perhaps an electron moves down from the conduction band to the acceptor, but the conduction band is empty. Why? Because, as we considered in the previous lecture, mu is somewhere in the middle of the gap, and getting a double occupation here makes no sense. So, I can't forget this state. Probability that we'll see such a population is small. Mirror picture here. We could have one electron moving up. We could have even considered 2 electrons moving up, but the fact that we'll have completely empty here is not reasonable because we're below mu. Okay, so these are the states that we are considering. This is a very simple system. It's a system with 4 states. Well, actually, ND times 4 states, or NA times 4 states, but we're considering them as independent impurities. So, writing down the occupation, does this need explanation? Hope not. Okay, so for the acceptor, I have 3 states, decided this one is not in the game. Sorry for the donor. ED minus mu plus 1 times E okay, I wrote down the 3 states that I'm considering. I'll sum up over this. Sorry, one thing. Here it doesn't matter, but here it does matter. The energy of no states is, no population is 0, not ED. Okay. Very similar to the usual fermionic behavior, up to this half, which comes that I have 2 states here for up and down. Okay, I can write down the same game. So this was for the donors. So I have this guy twice. One. Note its acceptor here. And after manipulation, but for the acceptors, we're not interested in the number of particles. We are not interested in the number of holes because it's under mu. So now we have all the ingredients. The conductance band, the donor states, the acceptor states, the valence band. We take it all and throw it together. It will make our notation a bit simpler if we'll use something that we have defined in the previous lecture. If you remember, we defined the occupation of electrons in the conduction, the occupation of holes in the valence, and Ni, which is just the number of particles moving from the valence to the conduction band. All these were equal if we had no impurities. But here we have impurities. Therefore, in general, can define delta n as how many more particles or electrons we have in the conduction band minus the number of holes that we have in the valence band. Okay. And we can what else do we know?
The multiplication.
The multiplication. What was the result for the multiplication? Okay, for the simple case that delta n is equal 0, nc is equal pv and equal ni. Here, not necessarily. If I have more donors than acceptors or I could have here a completely different situation with delta n not equal 0. So how do I represent it? Well, I can write here. In a moment, we'll define delta n as this, but I'm keeping it general because who knows, in the future I might use this equation in order for a situation, let's say I have a gate that changes the number. So I'll be general and then I'll use. So then, and I can, if I know delta n and ni, I can express nc or pv. Using them, so the plus and the minus are for nc or pv. So in our case, okay, if ND and NA are a small number here, I can easily solve this. So first of all, if ND and NE D minus NA is much smaller than Ni. Just assume this is much smaller than Ni, so I can forget about it in first order. And if ND larger than NA, Okay, what does that mean? Well, that is just a result of the manipulation. I think nothing more, nothing less. But what it tells you is that if the number of donors is larger than the number of acceptors, what will happen? Let's look on the picture, very simple. If I have here additional acceptors, first of all, I lose proportionally number of donors. Why? Because an electron that sits on the donor will head immediately to these states. They're much lower in energy. They're empty. The remaining ND minus NA will move to the conduction band. Mirror picture if I have more acceptors than donors. Same thing. If I have acceptor states here, first of all, these guys will go down and fill them up, but I have additional states empty. So guys from here will move to here, creating more holes in these states. Okay, so we understand what happens when we have homogeneous filling of these states. The main thing that happens, whoever is larger, the acceptors or the donors, will move to the respective bands. If I have more donors, I'll find those electrons in the conductance band. If I have more acceptors, I'll find these holes in the acceptor band. Now you can stop me and say, I'm sorry, I don't understand. This is lower energy. Why wouldn't they just stay there? right? But we're discussing here finite temperature. And in finite temperature, you have also considerations of entropy. You have much more states here than here. Therefore, for finite temperatures, you'll find these guys here, and mirror picture, these holes will move here, although it's a bit more energy. Okay, so we know exactly how to treat homogeneous behavior. X, and let's look on the situation where I have only donors to the right for x larger than 0 and only acceptors to the left, x smaller than 0. What additional physics comes into account from this picture? Didn't we treat acceptors and donors and we can go home? No, because the pictures that I gave you misses something. Okay, what is the picture that I described? Blue. The last of the blues. So well closed. Thank you. Okay. So what did I say the first what happens first when I described this picture? Guys from the donors go down to the acceptors. Then I check, do I have more acceptors and more donors? Okay? So what's the problem? I'll have here holes, meaning those electrons left, and they will appear here as electrons, right?
Probably not.
Hmm?
Probably not.
Almost right, but something additional happened. Remember, these are neutral electrons, neutral atoms, right? If I have here a hole, I have an ion that has a plus sign. If I have here an electron, I have an electron with a negative charge. So actually I end up with this region being positively charged. Why are they positively charged? Because these negative guys left to here. And this region is negatively charged because these ions have an additional electron. Now, if I separate plus and minuses, what does it mean?
You have a field.
I have a field and it costs me energy. Right? And I didn't take it into account in my whole consideration. Here I just assumed you have a constant energy for having a hole and a constant energy for having an electron, and that's all. Here it actually costs me additional energy to move something from the donor to the acceptor. Why didn't I consider it previously? Because if they are spatially homogeneous, an electron from the donor will go into an acceptor in its vicinity. So the electrical field will be relatively small. You can neglect it. But here I'm taking from one side to the other side. Costs me energy. So, physically, what will the system do to minimize that energy? If you want to separate plus and minus, and you don't want to pay too much energy, what do? Same things that you do when you take a spring and pull it apart. You pull it apart in a small measure. You don't pull it too much. Meaning that I might have this picture having some of the donor electrons moving to the acceptors in their vicinity near the interface between the two materials. But I wouldn't like an electron from very far in moving to an acceptor that's very far out there. It will cost me a lot of energy. So, what will I get here? A change in the occupation of the donors and the acceptors, and an electric field only in the vicinity of the interface. So I have a strong electric field in the region of the interface. When I'm moving out, nothing much happens. So everything is around the interface. Now what I have to do, go back to my statistical mechanics and take into account all these words that I said and put it into the calculation. So what is the additional ingredients that we didn't consider up to now? There could be an occupation of the donors and the acceptors which depends on position. And I have an energy that comes out from the separation of these charges. Okay, let's write down this whole description. So, the number of electrons in the conduction band. Why am I considering the conduction band? Because as previously said, any guys that's still here will move up. Right, that didn't change. Okay. So here I'm looking only on the conduction band and the donor band. And I'm saying, look, how much energy does it cost to have an electron there? You remember NC and PV are all the constants that don't depend on temperature that we considered in the previous lecture, times an exponential. EC minus mu is actually what we did until now, right? But now I have to take into account that moving an electron, because of this physics, could also cost me moving it in an electric field. So these are the phi x. I didn't say what it is, and I'll have to determine it. But generally, if I'll know how much electric potential energy it costs me to move an electron there, I'm okay. I've described the system, the energy. Just replaced EC with EC minus E phi. Same thing for the valence band. Okay. What else do I know? Well, I know another thing. If I'm very far from the interface, and now I'm thinking about an infinite system and an interface at 0. What do I know from our previous consideration about the population of the conduction band? Remember, here, very far away, I have no acceptors. A guy and donors that exist here will move to the conduction, and it doesn't care about acceptors because there are no acceptors here. It won't move from here to here, too much energy. So the occupation, the number of electrons in the conduction band, what will it be?
Number of impurities.
Exactly. Because here, everything that's here will move to here because of entropy considerations. It can't move down to the acceptors because they are so far away, will cost a huge amount of electrostatic energy. That's a and also one additional clue here. Okay, what is the difference in potential? Very far to the right, the energy of an electron that moved to the conduction band is EC minus mu, and if you remember, this is mu. Same thing on the left, but with an opposite sign. Question? Some of you. Let me rewrite it for it to be clearer. Let's forget a moment of this. Why can I forget about it, really? Number of impurities is very small. Let's look even for a moment on T close to 0. right? So it's just Eg for very small temperatures, right? So what does it tell me? The fact the total change in potential between the left side and the right side will be the change in energy of taking a guy from the left to the right. That's the potential, right?
But didn't we say that the field is only in the middle?
Right. But if I have field only in the middle, does it mean that the potential at minus infinity and plus infinity is the same? Let's go back to 11th grade and consider this minus, and I want to bring it to this here. I have here E equals 0, E equals 0, but I have here, because let's say a capacitor plate. So moving it from here to here, 0 potential. From here to here, E times D. From here to here, 0. So the difference in potential is times D, right? Same thing here. I have an electric field only in this region. But that doesn't mean that moving an electron from here to here doesn't cost energy, electrostatic energy, because I have to drag it through the potential. See what we did here. Once we consider the story in this way, like phi at infinity minus phi at minus infinity, right? Second picture, mental picture, we said, I don't know what's going on in between, but I know that the electron here was at EV, and the electron here was at EC. So what's the change in energy? EC minus EV, EG. And both descriptions describe what happens to the electron, moving an electron from the left side to the right side. Okay, and from this insight I can say something about delta phi. Okay, I'm doing electrostatics. So, a subject that we almost didn't touch on in this course, but still something that you have learned. How do I describe electrostatics where I have charges in the system? The Poisson equation, so our good old friend, the Poisson equation makes well, I don't think it ever made an appearance here, makes its first appearance in solid state physics. Not surprising, because until now, all the systems that we considered were essentially neutral. So I didn't need it. But here I have something that is the fact that I'm putting a different number of acceptors and donors at two edges of the system tells me that my system is not balanced in charge. So I have to take into account electrostatics. So I'm trying to answer the question, what is phi as function of x? The dialectic constant. Why are the acceptor and the valence band in plus? Because of this gentleman that decided in the 18th century to call the charge of an electron negative. Okay, this is, I didn't write down what it is, but it's the number of electrons at each position, which can be either in the valence or the acceptor or the donor or the conduction band. It looks daunting, but it's actually not so problematic. Why? Why does it make sense? Let's look at infinity. At plus infinity, what is the population of the conduction band?
MD.
MD. Okay. Same thing here. And going back to this definition, we get everything. Now we simplify a bit. until now, I didn't add anything. Now I'll add an assumption. This. The assumption is that instead of treating it the same all over, going through the equation, I assume that for distances from the interface that are larger than minus dp, or larger in absolute value, basically nothing happens here. For this region, you can guess what will be my assumption. Mirror picture. NC will be equal to ND, meaning, and this is an important point for me, what will I have here regarding number of charges, density of charges? What did I assume here? All the electrons, or the holes that were here, moved here, or all electrons from here moved here. What does it do to the net charge? Absolutely nothing. Because these guys moved locally. They moved from a state here to a state here. Lovely, but they didn't change the net charge in this region. These guys, again, they moved locally, didn't change anything. In this region, I assume all the electrons that were sitting happily on the donors move to the acceptors. Okay, what does it mean? point of view of rho x in this region. And lovely minus. If I have a donor in this region, it lost its electron, therefore it has a positive charge. If I have an acceptor, it gained an electron, and therefore we have an additional negative charge. What did I assume here? That all states here are empty, all states here are full. Of course, in reality, I'll have some change in the occupation at the boundary of this behavior. But then, what do I know? I have to calculate the electrostatic energy of this layer, compare it to EG. I finish the calculation. So, let me write down the piecewise behavior of phi under these assumptions. Okay? What does the Poisson equation tell us? On the left hand, we have the derivative, double derivative of phi. And on the right hand, we have the charge. So, I have here three, one, two, three, four regions. In this region we have no charge, right? If x is larger than dc, no charge. Okay. What is phi of x for these four regions? Okay, two of them are extremely easy. What is phi here?
You get plus,
Let's make it as simple as possible. Right? It's the same as in infinity, because no charge, nothing changes. Same thing here. No charge, nothing changes. To move a charge in a neutral zone doesn't cost me energy. Why? Because second derivative of this guy gives me this guy, and second derivative of this guy gives me this guy. It's okay at the left and right boundary. Now the only thing I have to worry about is connecting it at 0. Right? All the rest is okay. So I simplified by assuming a constant density. Because I've simplified, I got something that's easy to solve the Poisson equation for. Okay, so the only thing I have to worry about and I have two continuity requirements on phi and on the derivative of phi. So for continuity in phi, what does that mean?
the wall material is neutral.
Means that any charge that I took from here has been accommodated here. Because NA, which is NA is the number of acceptors per unit volume times D. is the number per slice is equal to the number here. Makes sense. Has to be. And continuity in phi using this relation. Just comes from equating these two parts.
Plus.
This is a good old friend delta phi. So actually, what did I really get from this continuity equations? What is the new physical ingredients that I put into the game here under this approximation?
The distance where something happens.
Right, I put in here two independent parameters that I didn't define. I said for some distance to the right and for some distance to the left, I get charge transferred from here to here. But what distance? This is exactly closed by this continuation equation. What do they mean physically? It means that if the difference here is large, I'll get a larger area of depletion. If it's small and the density of state and the number of states is small, I'll get a smaller one. So I can take these equations and pull out dc and dp. So this defines the size of the depletion layer. Why is the size of depletion layer important? Someone can guess?
Tells us how small can be our electrical components.
Exactly. The smaller that this region is, I can pack more diodes or more transistors into the same area. So, what can I do to make this region smaller? Basically, this delta phi is material dependent. It depends on the size of the gap. Larger the gap, smaller the region. And I could play with the doping. Sorry, smaller the gap, the larger the smaller the region. Why? Because larger gap, it will move charges from further away because it has a lot of energy to gain because of that. So that's why delta phi appears here. And remember, delta phi is simply the gap. And with the number I can play here. Okay, now what remains? Well, we have here a profile of potential. What do we know about a diode, or what you should know about a diode from your first year?
Passes current only one direction.
So I put an additional potential between here and here. In one direction, I'll have current flowing. In the opposite direction, I won't have current flowing. Now we have to understand it. That we'll do in the next lecture.